Welcome, everybody. Thank you for joining us in this event. I'm happy to host you on existing building assessments and retrofit and Turkey earthquake review. So our agenda starts today with preliminary discussions of the recent earthquakes in Turkey. We will then talk about the observations on the earthquake region. I visited Antakya, where the devastation was at its peak. So we will then continue with the overview of assessment and retrofit techniques in ProtaStructure. Then I will walk you through a CFRP retrofitted building that I have done in my postgraduate thesis study. And the building withstood 4 devastating earthquakes and countless aftershocks. So especially the assessment and retrofit part and nonlinear analysis part will be an overview. It's not possible to do a detailed training or detailed explanation in the limited time, but I will try to talk about the approaches in ProtaStructure. So I'm Mustafa Tan, and I have been working as product manager at Prota Software for almost 20 years now. I'm a structural and earthquake engineer by profession. Unfortunately, we experienced a series of devastating earthquakes on the 6th of February. And as civil and structural engineers, we acknowledged once more that how important our jobs is and how it is capable of, how our jobs are capable of destroying thousands of lives if not done properly, unfortunately. Excuse me. So before starting, I'd like to thank you, all amazing people around the world. Almost all countries extended their helping hand by deploying their search and rescue teams and sending us humanitarian aids. So thank you all amazing people. And we saw once more that there are no borders between the hearts of the people and how humanity can be at its finest at the dark times of others in need. So thank you all, and on behalf of the Turkish people, we are very grateful. So without further ado, here you see the past earthquakes about magnitude 7 in the last 100 years. So the 7.7 magnitude Kahramanmaraş earthquake is the second largest earthquake in the history of Turkish Republic after Erzincan in 1939. In terms of surface wave magnitude, intensity, and death tolls, it's the largest. The first earthquake had a magnitude of 7.7, a moment magnitude of 7.7, and the hypocenter was located at a depth of 8.6 kilometers. And 10 minutes later, another 6.8 earthquake happened. This was the first incident that caused the majority of devastation and collapses. And only after 9 hours, another 7.6 earthquake occurred in northern part of Kahramanmaraş, Elbistan, at a depth of 7 kilometers. And on the screen, you see, as of March 20, the death tolls are 50,000 people. We have 100,000 people injured. We experienced 17,000 aftershocks. They are minor, and the maximum magnitude is up to 6.7. 11 cities are affected. We have 20,000 buildings collapsed, and 10,000 search and rescue team members from 88 countries were deployed and sent to Turkey. I want to talk about the regional tectonics a little bit. I'm sure you are all well aware of it if you have done your research. The Anatolian microplate is moving to the west under the effects of African, Arabian, and Eurasian plates. This movement exhibits itself in the form of two major strike-slip faults, namely North Anatolian Fault and East Anatolian Faults. These recent earthquakes happened in the vicinity of Marash Triple Junction, where the Arabian, African, and Anatolian plates meet, and this junction is quite an active zone. That's what I'm talking about. Here you see the map of the East Anatolian Fault Zone. The major active fault segments are shown in dashed red lines, and the yellow dashed lines show reactivated segments during the February 6 events. The numbers in the rectangles show the year of the last major historical earthquake that occurred in that fault segment and the approximate magnitude. So based on the historical data, the fault segments ruptured during this earthquake sequence were seismic gaps with tectonic stress accumulated for at least 500 years. I tried to show them in red fonts. So let's have a look at the PGA contours, if you can see. So PGA or the peak ground acceleration contours are an important parameter regarding damage since it's directly proportional to the force. But of course, it's not sufficient. Since our buildings have a certain flexibility, our buildings can experience spectral accelerations greater than the peak ground acceleration. So peak ground acceleration is only a damage measure that we are using, demand measure. So white lines, if you can see on the screen, indicate the fault rupture, and the PGA values are specifically high in Antakya region, possibly due to the soil amplification. There is a particular, so I'd like to start with Hatay. Of course, Hatay was one of the mostly affected, mostly devastated cities, maybe the mostly affected city. So, but there is a particular station in Antakya which has very high spectral acceleration for buildings having periods from 0.1 seconds to 1.5 seconds. So this means that buildings in a very broad spectrum ranging from 2 to 15 stories are either collapsed or seriously damaged. This is a very high spectral acceleration. So I will not be including this record in the following comparison. Here you see the spectral accelerations for Hatay city center and provinces. Also, the collapsed and damaged buildings are shown. Hatay is the most adversely affected city among the 11 others. The city center is located on Amik Basin, which is nothing but an alluvial deposit. The Asi River is passing through the city as well. The city mostly has 5 to 15-story residential buildings, which seem to be the mostly affected as seen in the spectral acceleration spectra. The spectral accelerations exceeded the DBE earthquake, design basis earthquake, in the code, but they seem to be below maximum considered earthquake, MC earthquake, which has a return period of 2,500 years, and it seems to be below before 0.5 seconds periods. And the basin amplification effect is clearly seen after approximately 1 second, and even after 0.5 seconds for some of the stations. But of course, since all the buildings in Hatay, most of the buildings in Hatay have 5 to 15 stories, that means the majority of the buildings are affected. Here is another acceleration spectrum for a particular station that was able to record all 4 earthquake signals. the first 7.7 Pazarcık earthquake and the 6.4 Hatay earthquake 14 days later. And they seem to have considerable amplification effect after 0.5 seconds. Kahramanmaraş was one of the critically affected cities, being close to both of the earthquake epicenters. The spectrum for station, one of the stations here you see at the right, bottom right, is the station 4614. It exhibits 5 to 6 times greater spectral accelerations than the COT spectra between 0.1 and 0.5 seconds. This record is not currently in government website, AFAD website. Probably there is an error with the data and it will be restored back when corrected. But this means that 2 to 6 story buildings near the station will be damaged. But for confirmation, of course, the spectral accelerations in the Kahramanmaraş city center, the stations 4620 and 4615 are also plotted. Acceleration values seem to be fitting with dBE and MCE or code spectra, but still an amplification is observed after 0.5 seconds for station 4615. This means the buildings that are designed and constructed in accordance with new Turkish earthquake code should perform well. Old buildings or deficient buildings may suffer from the spectral accelerations as high as 1.25 G. And by the way, on the screen you also see the aerial map of the damaged buildings. The blue dots indicate slightly damaged buildings. The purple dots indicate heavily damaged buildings, and the red dots are the collapsed buildings. A similar scenario is observed for Gaziantep. In the city center, the code spectra seem to estimate the spectral acceleration demand well. The new buildings should not be suffering from collapse. By I mean the buildings that are designed and constructed maybe after 2007 and 2018, even after 2000, if they are supervised and constructed well. But on the graph, we see spectral accelerations as high as 0.6 G for very old and deficient buildings, for 2 to 5 story buildings. So for Islahiye, I mean 0.6 G in Gaziantep Merkez, I mean city center. So for Islahiye, which is one of the provinces of Gaziantep, 2 to 5 story buildings suffered from approximately a 2G spectral acceleration. In Nurdağ, another province, also the amplification is observed and high spectral accelerations are observed as you see on the graph. The code values were exceeded, but MC values still seem to estimate it well. The mostly affected buildings seem to have 2 to 12 story heights. For Adıyaman city center, the buildings with 0.1 to 0.3 seconds seem to suffer a maximum of 1.2 G spectral accelerations. After 0.3 seconds, a quick drop is observed. Buildings, again complying with the new, relatively modern Turkish earthquake codes, should be performing well in this scenario. But older and deficient buildings will be adversely affected from these accelerations. Osmaniye is another city that did not experience spectral accelerations higher than the code specified values. So 5 to 15 story deficient or old buildings will be affected from soil amplification. If you just check the period values between 0.5 and 1.5, you can just imply that 5 to 15-story buildings will be affected, which is approximately between 0.7 and 1.5 seconds. But still, the values are under MC earthquake. Adana seems to be an interesting case. Turkish earthquake, in Turkish earthquake codes, the observed spectral accelerations are under dB and MC earthquakes. So as you see on the graphs, the response spectra are plotted for the city center, and the acceleration values seem to be, spectral acceleration values seem to be low. Despite this fact, in Adana, 18 buildings collapsed and 85 buildings are heavily damaged, waiting for demolition. When you look at the collapsed buildings, you can see that they have between 12 and 20 stories. It may not be immediately obvious, but from accelerations, obvious from the acceleration spectra. But when you plot ADRS and spectral velocity graphs, it seems that buildings with 1 and 2 second periods seem to experience relatively larger demand in the city center. But still, these values are not too high to cause the collapse of these buildings. So as a result, we can maybe say that, yes, in some of the cities, the spectral accelerations were really high, especially when we have the soil amplification effects in Hatay or other Gaziantep, Nurda, or Islahiye. But we cannot say the same for all of the cities. The other cities seem to have relatively lower spectral acceleration values. That brings us another question, that whether these buildings were sufficient enough to withstand these seismic excitations. Of course, there are several reasons for that. So after this theoretical overview, I'd like to show you some of the damage and structural deficiency patterns that we had seen. So let's take a moment together and watch this aerial view that shows Antakya before and after the earthquake. So let's talk about the damages that we have seen on the site. So one of the mostly encountered failure or insufficiency regarding the material quality is the brittle failure of rebars. I'm not sure if you can notice in the screen on the screen. In reinforced concretes, we don't really expect the reinforcement bars to fail like a brittle chalk. These rebars are almost likely untested, and they seem to be not meeting the production standards in terms of carbon content. So they are either brittly sheared or just ruptured. So this is not the proper behavior from a rebar that we expect. So another cause, a frequent cause, was insufficient lateral stiffness. So the majority of the buildings that we have seen have insufficient lateral stiffness. So that results in, if not collapsed, a high damage in structural and non-structural members. Unfortunately, it's not a common practice in Turkey to use shear walls in the buildings. If used, the ratio of the shear walls to total area is not usually sufficient. So we cannot say that all of the buildings are frame buildings. We also have shear wall frame buildings in our country, but when you check the ratio of the shear walls, usually they are under a certain ratio. And of course, the wall dimensions in mostly residential buildings, wall dimensions are used in minimum sizes that are required by the code. Also, one of the reasons for that is the architectural design. The architectural design do not allow the use of shear walls, especially at the building perimeters. And this is combined with poor construction and poor supervision. And when you build a frame structure in such a country, not only Turkey, but it can be any country with a poor supervision and construction practice, the frame systems cannot withstand earthquake forces without any damage or collapse, because frame systems, as you're well aware, need to be detailed very diligently in order to sustain a ductile behavior. So that's the case. Unfortunately, there's the lateral stiffness is not sufficient. That there are very limited usage of shear walls. If they are used in a building, they are usually at a very minimum rate, at a very minimum ratio, and the dimensions are barely satisfying the minimum dimensions in the code. So these are two examples of a bad habit in structural system formation. First, due to permit reasons, and in order to enlarge the floor plan area, the commercial area at the upper floors, heavy cantilever portions are used in the structural system. And since architects are preferring a flat ceiling, this results in discontinuous frames, as you can see in the pictures. And because the frames are discontinuous, the building lateral stiffness is reduced because of that. So this is a typical floor plan that can be encountered in practice. The only shear walls are utilized in elevator shafts, and they are asymmetrically positioned at the edge of the building. And building floor area is enlarged at the upper floors using cantilevers. And this results in, again, discontinuous frames. You can see the beams missing on axis A, which creates an additional lack of lateral stiffness. So if you look at the displaced shape, the mathematical model of the building, it's clearly evident that this building has the first mode of torsion. So that's the example on the side. So torsional irregularity and mode coupling is a very important factor for triggering collapse. In this building, a rotational collapse is observed. It's also combined with a soft story, as it can be seen in the ground story columns. Most probably, the ground story was a commercial area with larger story height and without any masonry walls or shear walls. A relatively new construction suffered from damage. When we look at the shear walls closer, we can see the inadequate or non-existing wall end zone confinement. The lateral web bars are not anchored. There seems to be no end zones, by the way, and the lateral web bars are not anchored. And as far as seen from the picture, no cross ties are present. The wall itself seemed to suffer from high axial stresses, not only at the end zones due to bending, but also in its entire section. So the damage is observed when combined with inadequate detailing and confinement. Adjacent buildings are also very common practice in Turkey. Insufficient construction joints and mismatching story levels are primary causes of pounding damage. We have also observed settlement and liquefaction issues. The reason is, of course, due to construction on cohesionless alluvial deposits with high water table, without any ground improvements such as jet grouting, etc. Incidents of sand boiling are also observed, especially in Iskenderun region. This picture belongs to a famous residence complex in Antakya, which killed hundreds of its residents. Besides reported lack of detailing and material quality and segregation issues, the structural system seemed to have little tolerance for overturning. The 3 blocks are sitting on a common L-shaped monolithic basement, which is also considered to contribute to the collapse. And due to the aspect ratio of the building, which has a very slender floor plan, the structural system seemed to lack redundancy, especially against in its weak direction against overturning, and this combined may have caused the columns and walls to exceed their capacities and causing this collapse. As you see, the upper parts of the building, upper stories, do not seem to suffer from any damage. The building just simply toppled over. That's because of the high overturning effect and insufficient capacity of the ground story columns. Excuse me. So Turkey has a large old building stock. Most of our buildings are older than are built before the year 2000. So it was after 1939 Erzincan earthquake that the seismic effects started to be considered in the design of the buildings in Turkey. The 1975 earthquake code had provisions for seismic resistant design. In 1998, we had a relatively modern earthquake code, which is quite like UBC. It had capacity design principles to control the failure mechanisms and brittle failures in the members and in the joints. Then 1999 Gölcük and Düzce earthquakes happened. These were also devastating events which had 7.4 magnitude. In 2007, we had a new seismic code. The calculation of seismic hazard was same with the older code, which divided the country into 4 seismic zones. But it was the first time the codes had a dedicated section for retrofit and assessment of the buildings in 2007. Then in 2018, the seismic code is practically rewritten from scratch with a more detailed approach to seismic hazard. The seismic hazard map of Turkey was developed. Instead of seismic regions, we now have SS and S1 values, short and long period values for 15,000 data points. So seismic design and detailing chapters were revised, and we have now new dedicated chapters for seismic isolation. I tried to tell you about the evolution of seismic codes in Turkey, and also construction practice evolved in Turkey. It was maybe after 1995 we started using plant-based the concretes that are prepared in concrete plants and brought to the site. Before that, the concrete was mixed and prepared on the site by the workers. So this also has adverse effects in the concrete quality in the old buildings. Also, in the old buildings, it's very common to have straight bars with relatively less diameters used in links, or link spacings were used as 25 to 30 centimeters. So the construction practice also started to evolve after these years. So in summary, we still have thousands of buildings built before the year 2000, and also it does not seem feasible to retrofit them within economical limits. So in the pictures, you see one of the examples. For this building, the joints just could not handle the seismic excitation. So you can see the straight rebars or lack of confinement. And the picture on the right is a masonry building. And most of the masonry buildings in Turkey are unreinforced. They are slightly reinforced only in horizontal and vertical lintels. Lastly, I'd like to share a video footage that I captured from the car window in Antakya. So I want you to see the city with my eyes from the car. The entire city is in a similar condition. So to summarize, the deficiencies are the brittle reinforcement steel, low concrete quality. This low concrete quality is due to many reasons. First of all, in the older buildings, because of the construction practice in the past, the concrete was prepared on the site, not purchased from the concrete plant. So that was one of the causes in concrete quality. But in the modern, for relatively newer buildings, sometimes workers prefer to add water to the concrete, even if the concrete is brought from the concrete plant. So addition of water in order to make it more viscous, less viscous. So that brings us the low concrete quality reality. And regarding structural stiffness, we have insufficient lateral stiffness. Of course, this causes total collapse or pancake collapse, especially the joints, deficient joints. And also, if the building is not collapsed, the insufficient lateral stiffness is causing excessive amount of non-structural damage, so that the building is unusable. So another fact that we saw on the site, that there are little or no use of shear walls, and the detailing is insufficient in the existing shear walls. We have a lot of soft story irregularities because of the habit that this ground story of buildings are used for stores and markets, etc. And they tend to remove all the infill walls, all the infill walls on the ground story. And also for some of the buildings, ground story is higher than the rest of the story. So that's really an invitation to a soft story irregularity. We have seen insufficient ductile details, insufficient confinement in critical regions, or stirrups with small diameters, stirrups with 90-degree hooks. We don't have any wall end zones, or we have poor detailing. Straight undeformed rebars, and we have, in the old buildings, we see corrosion. We see all sorts of structural irregularities, and we have adjacent buildings with no seismic construction joints. But we also have standing buildings. The buildings that we have seen have sufficient amount of shear walls, or shear walls that are placed in the proper locations, so they prevented the collapse and they reduced the lateral displacement. And buildings with well-established structural systems still stood. Frame buildings with substantial column sizes like 80 by 80, and they seem to have seen good supervision. And also retrofitted buildings like one of the bank's buildings or the block that I will tell you about, they seem to be standing. So what's next? These are my personal opinions, of course. We need to have a professional engineering in Turkey, and our engineers, and I think all of the engineers in the world should have the knowledge and should have the feeling of structural system behavior. We need to have the ability to interpret and check computer outputs. Unfortunately, that's not the case in Turkey. Because of the complexity in the codes, because of the methodologies in the codes, doing a hand calculation, of course, is not possible. We have to use the computers, that's a fact, but we have to understand the methodology, and we have to be able to check the methodologies. The more complicated the code methodologies get, and the more difficult it gets to check the building or understand what's going on. Maybe in Turkey we should switch to a Chile model with a compulsory shear wall usage. And for the existing building stocks, we need to have effective and easy to apply retrofit techniques with safe and relatively safe and assessment methods. So these were my 2 cents about the earthquake in Turkey. Of course, specialists should comment on it better and further, and obviously further studies should be conducted on this earthquake, because these were maybe the biggest earthquakes in the history of Turkey. So I'd like to continue with the assessments and nonlinear analysis in ProtaStructure and the techniques that we usually use in practice. So ProtaStructure can conduct nonlinear pushover and time history analysis for assessment and performance-based design of the buildings. Of course, we achieve this by OpenSees integration. So the OpenSees, as you know, stands for Open System for Earthquake Engineering Simulation, and it's an open source software framework for stimulating the seismic response of structural and geotechnical systems. So nonlinear analysis requires a wide range of algorithms and solution methods. OpenSees provides nonlinear static, dynamic methods, equation solvers, and methods for handling constraints. So ProtaStructure analytical model is communicated to OpenSees via TCL files. In addition to the detailed analytical model, nonlinear material properties are also automatically calculated and added on top of this geometrical model. The entire structure is then ready for performance analysis. So for a successful OpenSees integration, considerable amount of pre-processing and post-processing is necessary. All the material nonlinearities have to be generated and sent to OpenSees. Column, beam, and wall sections can be modeled with fiber elements and analyzed with numerical techniques to derive moment curvature relationships in ProtaStructure. That's what we do. We are using confined and unconfined concrete regions, and strain hardening in steel can be taken into consideration. For more accurate analysis, you can even create the fiber mesh around the rebars. For column and wall members, a finite length hinge zone model is used with 6 integration points. Shear wall members are modeled with a distributed plasticity model, again with 6 integration points along their height, and force deformation relationships for integration points are obtained from fiber section analysis. On the screen, you see a sample of a moment curvature relationship we obtain in ProtaStructure using the fiber method. The single mode static pushover analysis is performed again using ProtaStructure OpenSees integration with the plasticity models that I have just described. Parameters such as number of steps and target displacements can be controlled by the user. After the analysis, we obtain the capacity curve. As you know, the capacity curve is a curve that describes the capacity of the building, as the name implies, and it is independent of the earthquake demand. So what we do, we allow you to select a node that you want to monitor. So you can monitor any node on the system and create the capacity curve for that node. And so we can extract the results at a certain demand point. And after finding the demands, we create a performance assessment report. So what I mean is, a vital step after obtaining the capacity curve is to find the demand that a target code spectrum requires. It's also known as the performance point. So the target displacement, in fact, identifies the performance point. So after plotting the capacity curve, a ProtaStructure can detect the target displacements according to FEMA 356 Euro codes and Turkish codes. Then we extract the values from that demand step and create an assessment report with the axial loads, shear forces, moments, and plastic rotations obtained in the certain point. A nonlinear time story analysis is the difference. The pushover analysis in ProtaStructure is a single mode static pushover analysis. That means as the load pattern, we are using the mode shape, the first mode, dominant mode shape as a load pattern. Of course, pushover analysis is a nonlinear analysis, and it can consider the hinge mechanism and redistribution between members. But it's still, since it depends on the first mode, it's not valid for all of the buildings. Particularly if you have higher buildings, or if you have buildings with coupled modes or less mass contributions less than 70%, or if you have torsional irregularities, even static pushover may not be applicable for the building. So in that case, you have to revert to a nonlinear time story analysis. It's also possible in ProtaStructure with OpenSeas integration. What we do, we allow you to set multiple ground motions and apply them simultaneously in X and Y directions. As specified by the earthquake codes, the ground motion application direction is rotated by 90 degrees and analyses are repeated. But of course, in selection of ground motions, parameters like fault mechanism, soil properties, and magnitudes are of importance. So before starting a time history analysis, you have to select the ground motions properly, which suits to your code requirements or project location. So, for example, in Turkish earthquake code, you have to select 11 sets of ground motions, and you have to use their average. But you cannot use them as you download from the ground motion database. So you have to scale them to your code spectra. So ProtaStructure also can help you in scaling these ground motions to a target spectrum. It follows a simple scaling algorithm between maybe 0.2 T and 1.5 T. So this is the very overview of the time history analysis. Of course, we have all the material non-linearities applied on the model, and then we send all the data to OpenSeas for the analysis itself. And after that, okay. After that, we post-process the results for maximum and average responses. Remember that we cannot use only one set of ground motions. We have to use maybe 11 ground motions. So extracting maximum negative and maximum positive responses from these data sets for each time step, and preparing them and harvesting them for a proper assessment report is quite time consuming. So ProtaStructure can do it for you. So here you see some of the examples that some of the screens that you can see in ProtaStructure. And also at the end of the building assessment, to visualize the assessment results, you can color code the member damage regions in the 3D model. So to mention a little bit about retrofit techniques. So first of all, retrofitting existing buildings may not be feasible for all of the buildings. So if the cost of the retrofit exceeds 35–40% of demolition and rebuilding the structure, then it will lose the feasibility. So if the building is, of course, a very valuable building and you cannot just give up the building, of course, retrofit can be a viable solution. One of the most utilized retrofitting strategy is to use reinforced concrete walls inside the existing frames, or you can just use eccentric shear walls that are attached to the exterior of the building, as I will explain in my case study. This method improves the overall lateral behavior of the existing building, but you have to apply this method from the foundation to the top of the building. This is called a system retrofit. It doesn't focus on individual members. Rather, you have to focus on improving the condition of the building, especially the lateral stiffness. So in ProtaStructure, you can insert retrofit walls in your existing structures. Modeling the existing structure is, of course, no different than the new buildings. You just insert your columns, beams, you just define your existing reinforcement, existing material. It's like modeling a new building. Then you just select the locations of the retrofit walls. Then you perform an assessment analysis on the structure. But of course, these retrofit walls should be detailed in a different way, since they are built in between the existing frame. We have to calculate top and bottom dowels and right and left dowels, which ensure that this retrofit wall is integrating well with the existing system. So this dowel calculation is important. Also, there's a certain way of detailing in these retrofit walls. Another common approach is to apply reinforced concrete column jackets, but jacketing can be considered as a member retrofit rather than a system improvement. It's focusing on individual members. So the first reflex of the engineer should be to improve the lateral system rather than focusing on individual members. So an RC column jacket can improve the axial load and moment capacity of the existing column. So if you can improve the moment capacity only if you extend the longitudinal bars into the upper story. So that means you have to drill the slab and extend the bars to the upper story. This is an option in ProtaStructure as well. If the existing column is too damaged or weak, you can also delete the existing column from the model, so you don't get any results from the existing column in the assessment report. That may be usually the case because when you insert a jacket, then of course you apply dowels in the existing column as well. So That means the jacket and the existing column starts behaving in the same way. So they are integrated together. So maybe it should be considered that way. Another popular retrofitting technique is wrapping the columns with CFRPs, columns and beams. But it's again similar to jacketing. It's again a member retrofit rather than system retrofits. So in ProtaStructure, you can insert this retrofitting scheme to the members. What it does for the columns, it increases the shear capacity and axial capacity because it provides additional confinement to the column. And for the beams, it increases the shear capacity. Now in ProtaStructure, you can consider these effects. Another retrofitting technique that can be considered is the base isolation, but usually we do not use base isolation as a means of retrofit in most of the buildings, because first of all, if the building is too weak or the lateral system is too deficient, it may not be feasible or it may not be practical to install these isolators. So in order to use the base isolation, the building should have a high economical value. So it should be approached with caution. But you can use the base isolation as a retrofit technique. In fact, we have applied this to one of the hospital complex in Istanbul by using ProtaStructure. So all the existing columns were cut and isolators were installed. But this was a relatively robust building, which was built in 1999. So and the building to the right, you see the curved building like a boomerang is a new building that's built with isolators. In ProtaStructure, you can insert seismic isolators anywhere on the columns, since the base isolation is not necessarily at the foundation level. You must have decided on the isolator units and isolator layouts and lateral and axial capacities of the isolator units before modeling them in ProtaStructure. So this is an example section from the seismically isolated hospital. So the yellow ones you see are the isolator units applied at the top of the columns in the basement, and the red ones are just like sliders, roller supports, which have very little lateral stiffness. So as I've said, you can model seismic isolators in ProtaStructure. This is a screen capture from ProtaStructure analysis model. But as I want to emphasize that you have to decide the isolator type, isolator layout before modeling them in ProtaStructure. ProtaStructure cannot perform a nonlinear analysis with the isolators. So after selecting the isolator types and after introducing their equivalent stiffness values in the model, you can perform a linear elastic analysis in ProtaStructure. Okay, so these were all about I wanted to say on retrofit techniques and assessment techniques. Of course, this is a very detailed topic, so I can only give you an overview of ProtaStructure's capabilities and overview on the analysis methods themselves. So if you would like to hear more on assessment methods or seismic isolation, please write to us, or at the end of the webinar, you will have a survey. If you want to hear more about these topics, please just send us a message or just write a message that you are interested, so we can organize other sessions focusing on these topics as well. So in the last parts of the webinar, I'd like to talk about story of a building that survived the earthquakes. It is the Antakya municipality blocks, the A2 block. It was retrofitted in 2009 as a part of my master thesis study. It was a team effort led by Professor Güney Özcebe and Professor Barış Binici, and I was lucky enough to be included in the project, so I applied the theoretical background that was developed in the lab experiments and nonlinear studies, and I was able to apply that retrofit technique on an existing structure. So we had a 50,000 euro financial support from NATO as well. But as you see in the pictures, the building was quite old. It was built on 1974. It's now like 50-year-old. We had severe corrosion in the basement, in the ground story, and even in the first story. So all the bars were straight bars. We had no confinement, practically no confinement in the support regions, 25 centimeter link spacing with 90-degree hooks. So this was the situation. The building practically did not have any ductility that would allow it to withstand the plastic demands. And also, maybe the most obvious deficiency in the building was the soft story. If you take a look at the ground story, you will see that it has a 5-meter height. So the remainder of the stories are 3 meters high. So the ground story was 5 meters. So it was an obvious soft story and we immediately saw that if the building was to collapse, it would be due to the soft story. So what we did in the building. So on the screen, the red things you see on the screen are the shear walls. We applied the shear walls on the exterior of the buildings, and in the middle we selected some of the infill walls and we applied FRP strips. So we applied them in the manner of a compression and tension ties, and we anchored the FRPs to the existing frame joints. And also we had surface anchors that will bind it to the other side of the infill wall. So we wanted to provide as much lateral stiffness as possible to the building by applying reinforced concrete walls and CFRP retrofitting. So the walls themselves were not enough to satisfy the Turkish Earthquake Code 2007 life safety conditions. So that's why we also put the CFRP infills. Sorry. So you see some of the pictures from the construction. So first of all, the purpose of the study was to show that we can retrofit a building without relocating the residents to other places. So all the construction work was conducted while the residents were inside the building. So they just tidied up their goods, and that's all. So the eccentric shear walls were built outside the building, but pay attention that we anchored them to the surface of the members, and we anchored them to the slab level where most of the inertial forces are transferred. So they are anchored to the system. And also we had corrosion repairs. So what we did, we just cleaned all the concrete cover, we cleaned up the corrosion, we applied chemicals, and we just wrapped the column with the FRP to further reinforce it. And also inside the walls, as you see again in the picture, we applied diagonal FRP strips to allow the wall to act as compression and tension ties in the case of a lateral load. So in this manner, the infill wall is turned into a composite material that can resist in tension and compression. So the FRP strips were anchored to the existing frames in the column and beam joints, and also we had surface anchors. So this was the time I said goodbye to the building. I visited the site. Most probably this building maybe will be demolished because there are structural damages as well in the building. There are some coupling beams that are damaged from shear, and also because of some production issues, there were some captive column damages in the building as well. But and also these were three blocks. We had one first block, second block, and a third block. We retrofitted the second block. The third one, unfortunately, immediately collapsed during the event. The first one is heavily damaged, but the only retrofit the first one had seen was the FRP rewrapping around the columns in the ground story and the infill walls again in the ground story. But the second block that we retrofitted did not suffer any heavy damage. We can say that it satisfied the life safety performance level, while the slightly retrofitted first block was satisfying the collapse prevention. So this was the story, the very brief story of the building that I retrofitted as a part of my master's study. So this ends my presentation. Thank you so much for reserving this session to me and for your participation. And before finishing the webinar, maybe I should have a look at the questions pane. Thank you so much for your attention and reserving your time and for staying with us. This was the topics that we wanted to talk today. I hope we will not experience disasters like this in the future, and we can take sufficient precautions and sufficient care to prevent these deaths. Thank you so much, and hope to see you in another event.